Hello everybody, welcome to the second half of session 5, which is all about cheating in nonlinear buckling. Now, because we had some internet problems, what I've done is record the main presentation and then I've recorded the questions that came through. I was able to cut and paste these out, and we've got 22 questions, so I've been able to curate them, lay them out, and then apply the answers. So I hope you enjoy this. 22 questions coming up now. Thanks very much. So the first question from Christopher: practically speaking, isn't all buckling non-linear? Well, yes, you're absolutely right, Christopher. Really, it is all non-linear. But again, with like a lot of non-linear analysis, if we can simplify to a linear state, then that's quite a useful thing to do. So in this particular case, we could perhaps simplify to linear buckling. We talked about that in the presentation. So if the physics allow it, then we can simplify. In that particular case, it will be because the slenderness ratio is large enough so that Euler buckling, or if you like slender buckling, is going to dominate. So in those kind of situations, I think we're justified in simplifying. Josh asks the question that instead of using a cheat side load, could you use a simplex asymmetric mesh to introduce a small instability? And I've certainly seen that happen. Sometimes we don't actually want that to happen. We get a non-symmetric response perhaps initially because we've got a non-symmetric or an asymmetric mesh. So it might well be the case that putting a perturbation and stiffness in the material, because the element is slightly distorted, the mesh is slightly different, is enough to actually trigger that instability. It's an interesting idea. I've usually tried to avoid it, as I said, trying to get a symmetric response, but by deliberately putting in a non-symmetric mesh, you might well be able to achieve that. Ivor has an interesting observation that he's seen that pushing a little side push on the second eigenmode, maximum deflection point, we get the best switching from one buckling shape to another. Yes, if you're switching back perhaps to the first buckling mode, so you're deliberately going to the second one and then pushing through to the first one, it's kind of proof of that stability that we really want to achieve that first buckling mode. A little bit like I went from mode 6 back to mode 1. So I certainly would recommend trying different buckling shapes, different mode shapes, different imperfections, initial imperfections, to see if they will converge towards the same final buckle shape. It's an interesting idea. So thanks very much, Ivor. Sven asks the question: what would the deflection curve look like if you subtract the deflection from the side load alone from the total deflection? So this is going to be the side deflection. And the idea is that that push load, that cheating load, shouldn't really make any difference to that lateral deflection. So if we took the influence of the lateral deflection away, we shouldn't really see much difference in there. That would be an excellent check to make sure that we haven't kind of contaminated the result. That's why I kind of finessed that cheat, kind of brought the load down, so the load is 0 at the end. So it prompts the action, but it shouldn't start to really influence the resultant action at all. So ramping it off is a really good check. We can also check the level that we're putting in there to make sure that we don't unduly influence what's going on there. Marina asks the question: do linear mode shapes really tell us anything? I thought it's only the Euler load that is a valuable result. The Euler load certainly gives us the scaling factor, which gives us the critical buckling load. The mode shape gives us some indication of what the possible resultant buckle shape is going to be. We know we can't put any level of amplitude on it, it's just an arbitrary scaling. And it might well be that we get a transition to something else, but it is useful for that initial indication of what could be happening. And it's also useful perhaps to be using as an initial imperfection, for example. So it is useful. We've got to be very careful with it, though. It is giving us a clue. It might transition to something else. The amplitude levels, the displacement levels are meaningless, and because we don't add the stress state from the axial loading to the perturb loading, again, the stresses and strains are completely and utterly meaningless. So you're right up to a point there, Marina, but it still has some use to look at those mode shapes. Lewis asks if I could explain more about the thickness on page or slide 18. Did you mean to use wall thickness as the first approximation of the lateral displacement to induce buckling in the FEA solution? And that's pretty well what we're trying to do there, Lewis. So the idea is I roughly think of that initial perturbation, either due to load or putting in the deformation, to be round about the order of the wall thickness. It might be a fraction of that. We might go down, get successfully down to maybe a fifth or something like that, but it's around that sort of figure. If we make that lateral displacement too big, then if you think of like a cylinder with, say, rippling in the cylinder, longitudinal rippling, that actually is going to cause, if we magnify that up, almost like corrugations. So there would be stiffening the structure up. So if we make the displacements too big, many times the wall thickness, there's a chance we're actually going to stiffen the structure. So we just want a little bit of displacement to get us going, and then the actual buckling will take over there. Ryan asks the question, am I running with explicit or implicit dynamics or RICS to get the post-buckling event response? All the analysis done in the presentation have been implicit analysis. They've actually been static, non-linear. So basically we've been getting static equilibrium at each load step, and we haven't been bringing the inertia terms in. You get slightly different response, and you could argue that most of the fast buckling modes are dynamic, but it's very common just to assume that we can actually get a static equilibrium as we go through. To get that post-buckling where I actually chased the structure down and had softening, there I use the RICS, which is like an arc length method where I can actually unload the force to actually chase the buckling down. James asks a very good question. How do you know which direction to initiate the buckling? For more complex models where a buckling object is incorporated into a larger body, you may or may not know which direction it's going to buckle, which could give a different result. You're absolutely right. For a linear buckling, it can buckle in either direction. So, for example, our strut could go either way. For the nonlinear in that particular case, also because it's pretty well a symmetric structure, it could go either way. But if there was some symmetry or asymmetry or lack of symmetry implied in the overall structure, it might be quite critical as to which direction that loading direction, that kind of push loading was going to go. And the only way to do that is perhaps we could see intuitively, or just basically try to approach us. Again, it's looking at this sensitivity of the loading form. There it's the actual direction, as well as we've looked at magnitude and position. So there we'll be looking at direction to see if it made any difference to what the answer was going to be. And if we found there was a difference, we'd probably be taking the lower bound and saying, well, this is the most conservative direction to take. So yeah, in many cases, it's actually trying to track the physics is quite tricky. We sometimes think of this point where it starts to buckle. It's almost we've reached like a peak. At that point, we're about to leap off the peak. Which direction do we take, or which direction do we travel down? Perhaps if we're skiing would be a better approach or analogy. Which path are we going to end up skiing down? We don't know. It could be one of many. We just unfortunately have to explore it and see what seems to be the closest to reality. Manuel asks, is there a minimum load factor to be considered when making linear buckling analysis? I'm going to take this to mean we, for example, apply 1,000 unit load, newtons or pounds, and then our eigenvalue is going to be a scaling factor on that. I normally like to take something which is going to give reasonable numbers, so like 1,000 unit with say an eigenvalue of say 0.1. What I don't like to do is just put in a force level which will give say an eigenvalue of 0.0001 or the other way around. So I like to kind of get healthy numbers in there simply for rounding error problems. So if we've got an eigenvalue of 0.1 operating on 1,000, that's great. If we've got 1e to the minus 6 operating on like 1e to the 7, then that would be perhaps a little bit suspicious or not a good thing to do. That's what I've taken as being the meaning here, Manuel. If I misunderstood, again, please just send me an email or contact me on LinkedIn, and we can kind of explore that further. Ricardo asks, is the rule of thumb to choose the lateral load's magnitude Sometimes I just try something, like I think I had about 2% of the loading in that strut and it seemed to work, so that's a very low level of loading. I didn't really bother to explore it any further. Other times what I do is to say, well, the value of the of that lateral load, what deflection would it give as a static analysis? And again, we've got that maximum deflection we want to see of around about the order of the thickness. So whatever load level that is, that's kind of typically what I would choose. If it's a thick, beefy structure, then that's a little bit more difficult to kind of figure out. And then I would be looking for something like 0.1%, maybe 0.01% as my starting level. Something which is so small that the stresses are not going to be influenced by the presence of that spurious loading action. And here's a similar question coming from Mentor. Are there any guidelines or checklists on the amount of imperfections to be used for non-linear buckling analysis? For something with a thin wall, then again, maximum would be of the order of that wall, maybe dropping down to say a fifth or a tenth. If it's a thicker, chunkier type of structure, as I just mentioned, maybe again we think about the local stresses that we built up by that spurious loading. We want them to be very, very small compared to the overall stress state that we'll be developing due to our buckling load. Here's a similar question from Ricardo that we've had previously. How can I choose the perturbation load's direction when dealing with complex structures, not knowing what the buckling direction will be? If we truly don't know, there's no intuition, then unfortunately we have to try, say, several directions, and again we'd be picking off the lowest buckling load as perhaps the most conservative that we can use there. Brijesh Ras asks, rather than using a side load, is it okay to apply imperfections, and how does that affect the matrices, the stiffness matrices? If we're talking about nonlinear buckling analysis, then certainly we can use either approach. And what we would hope is that the general geometric nonlinearity or the geometric nonlinear stiffness we're developing in the nonlinear buckling is going to become a very similar path. So as we change that stiffness, the load deflection curve, which is effectively the tangency of that, is the stiffness change, is going to be similar whether we start from a loading or whether we start from an imperfection. Again, a similar question from Michael. How to decide the side load is not too small and not too big? Well, if it's too small, then I guess we're not going to actually start to initiate buckling. So if we are so small with our imperfection, our push, our cheat, if you like, is too small, then we're not going to get a nonlinear buckling. And that sometimes happens. We've kind of undershot it. Too big is a little bit more difficult to kind of figure out. All we can do there is a sensitivity study to say, well, this has created buckling. We carefully look at the level of deformation that will be implied by the side load, look at the kind of the runaway, the deviation from that, and try and see if we've made any influence there. Again, the only way we can really do that properly is to do a sensitivity study, basically back off that load level and to make sure that we actually see a consistent response from the structure. If we see the response to the structure changing as we reduce that load level, then the load level is going to have been too big because we've been influencing that buckling. A question from Nick. As I mentioned, when plotting load versus deflection data from a nonlinear geometric model, there's a transition zone. Is there a general rule of thumb for what value to pick as the buckling value? You could argue that you want to be very conservative, and as soon as you get any deviation away, say from a linear path, then you could pick that, but that's usually, I think, over conservative. It's actually quite a big topic. There's quite a few ways we can try and get better on that. One way is to actually get a very accurate number of steps, so we get an accurate curve, fit a polynomial through that, and then take the first differential of that polynomial and then the second differential of the polynomial and try and see if we can see some sensitivity in the what will be the rate of change of the deflection with buckling load. It's rather like the difference between a displacement and an acceleration. We may see a sensitivity there. That's one approach. Another approach I like to do is to try and pick somewhere where the stresses are going to transition, say from membrane, mainly compressive, to bending, and then sometimes we can get lucky, we can really pick out a rapid transition as that bending stress locally kicks in. So we're almost kind of finding like a virtual, not a strain gauge, but like a like a stress gauge point to show us, hey, this is where it's transitioning. Something like Snapster have had very good success with that. The third approach is to actually take a point where you think very close to buckling, and then you can say, well, this structure, let's take the stiffness terms associated with this, and then carry that forward into a linear buckling analysis, where it's a small perturbation analysis, but this time it's a linear perturbation on what is our baseline nonlinear model, and we may then find an eigenvalue solution there. I don't like that one so much, but again, that is sometimes used. So it is a tough question. So there is a variety of answers there. I'm afraid you're going to have to kind of pick your way through that. It's a big topic. It's a very good question. Here's a great question from Randy. If you're a designer and your concern is only whether the beam fails, bends with plastic deformation, would an elastic approach with a safety factor be more than adequate? And this is done in quite a few industries, and I think the approach is often called like a knockdown factor. So we would run a linear elastic analysis, or indeed perhaps even do a hand calculation, Euler type of calculation. We know that we're going to overshoot that safe region, the slender region, but because there's enough work had been done, maybe the Johnson equation also has been used, or there's test data, for known sections there's a known knockdown factor to basically bring us back down to, if you like, from the Euler curve back down to the Johnson curve. It's okay as long as we are confident in these knockdown factors. So I think from a designer's perspective, we're just looking for a quick answer. This would be a great approach. But again, you've got to be within that safety zone where you think that knockdown factor is going to be appropriate. I wouldn't ever like to guess one for a structure which has not been through that kind of process. It's kind of out with the standard sections and so on. But again, a great question. You might well develop your own knockdown factors by comparing linear analysis and nonlinear analysis for a class of structures which you're always going to be using. You might become like the world expert on knockdown factors in that particular kind of case. I would also hope to be bringing in test as well as just nonlinear analysis as well. But a great question coming from a design perspective. Here's a question from Erwan. For nonlinear buckling analysis, say for a skirt support pressure vessel with skirt hole opening, is there any difference on result with a different location and perturbation load, for example the point near the opening or further away from the opening? And that's a very good point. I think rather than trying to get an overall buckling mode there, which we might check with an overall mode shape or an overall perturbation, I'd also be very tempted to be putting in local perturbations, maybe like a local pressure load. There are other ways of getting what we think would be a typical defect locally. So sometimes the local modes, the local deformation is going to be more important than the global. We need to be checking for the global all the time, but I think that would be a great case for bringing that in. It's rather like that slide I showed where we had the dimpling on the rear end of the aircraft. That's what we're trying to model specifically. We're not particularly interested in global modes there. It's the local modes, and hence deriving forces or some way of getting those little dimples in as initial imperfections with our kind of push loads or our deformations, whatever we want to use there. And I think this question from Yunksin follows exactly the same thing. To introduce a real defect, such as a pore, for example, which is in a particular location, yes, we want to be looking at the local modes which are going to be a result of that. Again, always at the back of my mind of checking global modes just in case it's going to propagate an overall collapse, but certainly the that local modeling is going to become important. Now here's a very interesting question from Mode. If we use a slightly deformed beam to allow that small moment to build up in linear buckling, do you think the critical buckling load will be a lower value closer to the linear buckling solution? You're essentially putting, like in the Euler equation, you can put an eccentric load in. So to that extent, yes, it's going to lower the critical buckling load. Will it be the same as the nonlinear buckling solution? That's a very good question. There is a method, I think it's called the P-delta method, which is an old method which does a series of linear solutions which kind of figure out, okay, we apply this eccentricity, get this deflection, and then run a linear analysis to say, a subsequent linear analysis to say, let's apply this load or increasing load to that deflection, and then it's a kind of a, it's like an iteration in that way, or it's a chasing a particular path. But what that's missing is the geometric nonlinear change of the structure, because each time in a linear buckling, it's just really, as we've said, it's just linearizing. It's not actually putting a geometric nonlinear term in there. So the P-delta method, I think it's called the P-delta method. Some people, it's a simple kind of approach, hand calculation approach, but I think it's a little bit dangerous. It's going to get some level of eccentricity, some reduction in the critical load, but your question is it close to the nonlinear buckling solution? Some cases, I think, for simpler structures, maybe. In other cases, I think it might drift away from wherever the true geometric nonlinear effect, which we're getting in the nonlinear buckling solution, is playing a role there. But it's an interesting question, and I think if you look up I think it's called the P-delta method as a reference, you might find some other insights into that. Zhao Fai asks a question which really goes back to one of our earlier points. May I ask how to determine the exact buckling point in a nonlinear buckling analysis? Again, that's rather tricky. We can be conservative and take the first major deviation away from the linear path, where the curve starts to, as the lateral deflection starts to increase, or we can use a couple of the other methods I talked about to try and nail that down. But that is a very difficult area, and the motivation again is we'd like to get one number. So if we can say it's like 1,500 pounds or 2,000 newtons, we can put perhaps a margin on that. It's not always satisfactory to say it's somewhere between here and here, so people are always looking for that number. But it's a very difficult question to answer. So again, it's a tricky one. Good question. Vivek makes the comment, I used to take normal increments of load up to a load smaller than the buckling load, determined by linear buckling, and then switch over to smaller increments to cross over the buckling load, and also switch over to the arc length method of stiffness update. This is a very good point. It's part of the nonlinear strategy we teach on the nonlinear e-learning class. If we can break the load into two segments or two parts, so we get up to just before buckling occurs, then that's almost like we've achieved a base camp. We're satisfied, we're happy, we've got to that point. And then we can explore different routes from that point, or different attempts. And one of them is a very good idea to switch over to certainly to smaller increments, so we can tiptoe up to the buckling load. But also we can change different solution strategies. Like you mentioned here, changing to the arc length method. We can change convergence values. We can do a lot of sort of numerical experimentation, but starting from close to where we are. So I often call it like the kind of the base camp approach. We've achieved something, we keep hold of that which is close to the buckling load, and then we explore that. I sometimes call it that peak where we're going downhill. What path do we go downhill? So you can either think of a base camp, I guess, going uphill, or skiing downhill. Which path do we take? So it's a very good point. Nonlinear solution strategy where we're splitting up the load into major increments so we can change our tactic or change our strategy is a very good approach. So here's the final question from Ken, and in many ways it's perhaps one of the most intriguing. How to analyze a cooling tower wind pressure load, Fourier number equals 1. In other words, basically like a sinusoidal distribution, let's say, around the perimeter of the cooling tower for buckling. Can we use symmetric, would just be like a compressive, or rather a pressure load constantly, plus axial weight? That's going to depend on if the cooling tower's buckling mode is independent of the wind pressure distribution. If it's basically the wind pressure distribution is giving a small kind of perturbation, and then it's the axial loading which is causing the collapse in a symmetric manner, then I guess we could get away with it. I don't know enough about cooling towers, but I think I see what you're trying to do there. It's whether, again, it's that initial perturbation is going to migrate to a symmetric response. If it is going to migrate to a symmetric response, it would seem to be a reasonable kind of approach. If it's going to be a non-symmetric response, then we can't use that type of approach. Again, a very interesting question. It raises a general point. We have to watch out for non-symmetric responses in buckling of symmetric structures, or here's an axisymmetric structure. In the old days, for FEA with coarse meshes, with hand calculations, if you forced a symmetry boundary condition in a mesh, you are forcing a symmetric response. Equally, simplification of hand calculations did the same thing. There was a bit of a period where it was realized that these answers were wrong because of the enforcement of the symmetric boundary condition. So it is a tricky area. Without trying it and looking at the physical implications, it would be difficult to answer your question. But it's certainly a good idea. It's something worth thinking about and worth exploring. Well, thanks very much for all those questions. That's 22 questions we got through. It was a very interesting set of questions indeed. So I hope you found those useful, and indeed we look forward to seeing you next time. So this is going to be, in fact, this Friday coming, when we're going to be talking about high cycle and low cycle fatigue. So hopefully plenty of questions coming through from that, and we'll see you next time. Thank you very much, everybody. Bye-bye.